Okay. Um, Good day. So, our topic now for today's discussion is still engineering, sciences, and allied subjects, but uh, the content now of this lecture will focus on mechanics of deformable bodies, or others may term it as strength of materials. Okay, so um, again, um, you can like and subscribe no so to this page, and uh, turn on the notifications, so for you to be notified if there are um, other new lectures that will be uploaded. On the other hand, you can have our books to supplement your studies, either in engineering mathematics, engineering sciences, um, and might as well with electrical engineering professional subjects. So we also have the RME, a review book. Uh, you can visit, no? So you can visit our online store. Okay, so uh, for cash on delivery basis, or you can always email at acdcengineering2013 at gmail.com for bulk orders of these review books. Okay, so we will be starting right away the discussion for uh, the topic. Okay, so the first topic that we will be discussing will be about stresses. Okay, so basically we'll be focusing into simple stresses, so which is defined, no? So stress is defined as the force divided by the resisting area. So for rigid bodies, we often use not so the term stress, but for fluids, we use also the term pressure. Okay, so both stress and pressure can be expressed as a unit force over the resisting area. Okay, so commonly we have the two units now for stresses. So we have the pounds per square inch, or PSI, and we also have the Pascal. No? So Pascal, which is equivalent to Newton per square meter. Okay. So for simple stresses, okay, okay. So we have three. So we can categorize the simple stresses into three types. So we have the first one. So we have the normal stress. Okay, so the second one, so we have the shearing stress. Okay, and lastly, third one, so we have there the bearing stress. Okay, so both of them, okay, both the normal, the shearing, and the bearing stress will be given as force divided by unit area. Okay, so we will say that the normal stress denoted by the symbol, and then we will have the shearing stress denoted by the symbol, no? So with the subscript S, and also we denote, no? So bearing stress as force per unit area. However, it must be noted, no? So that since the definition of stress is force over the resisting area. So we have to identify uh, what area no, so is meant by each of the formulas presented. So for normal stress, okay, so for normal stress, so we often define A here as the, so this is the perpendicular area. So this is the area which is perpendicular to the applied force. Okay, so it okay. So one must be able to identify, no, so as to uh, which area is being focused in the question or the problem. So will it be the perpendicular area, so which is the normal stress, or for the shearing stress, so we define A as the parallel area. Okay, so that is the area parallel to the applied force. Okay, and also for the bearing stress, we define A as the projected area. Okay, so later on, we'll be showing some uh, figures as to we can identify, no? So which of these, or we can illustrate, no? So the difference between the normal stress, the shearing stress, and the bearing stress. Okay, so just always remember that for normal stress, so we refer the area to be the area perpendicular to the applied force. For shearing stress, that is the area parallel to the applied force. And then for the bearing stress, we term area as the projected area. Okay, so that is just the difference between the three uh, normal stresses. No, so it is actually the area that is being considered. Okay, so normally, if the question or the problem is asking for the stress, so uh, one must have to look at the given area. So whether it is perpendicular area, the parallel area, or the projected area. So that you can identify what type of stress is being asked, no, in the item or the particular problem. Okay, so you will be shown. Okay, so in the next okay, presentation about the difference, no? So we have here the normal stress or the eggshell stress. Okay, so as you can see, so the area being considered is the area that is perpendicular, no? So perpendicular to the applied force. Okay, and then on the other hand, we have here the shearing. Okay, the shearing stress. So this is also called tangential stress. So we consider here the area which is parallel, no? So parallel to the applied force. Okay, so just like in this example, so you have the two uh, plates, for example, no? So which is subjected by a force F, no? Each plate. So the area that is being given in consideration, no, with the shearing stress is the perpendicular area, which is the circular area as shown, okay, which is the uh, area parallel, no, so to the applied force, assuming that the joint, no, so the slap joint is the one that holds the two uh, plates, no, so we consider the area, no, or the cross sectional or the circular cross sectional area of the uh, lap joint. Okay, so that is for the shearing stress. And also, if we try to consider, no, so we have here the bearing stress, no, okay. So try to look at, no, so the bearing stress, the area that is being considered is the projected area. Okay, so the projected area, so it's given by the shaded area as shown, no, in this figure or this illustration. So we define, no, as you can see, we define each of the stresses, no, as force over area. So, however, the area, uh, okay, the area differs actually in each type of stress. So for a normal stress, we have there the perpendicular area. So for the shearing stress, you have there the um, parallel area. And for the bearing stress, we have there the projected area. Okay, so now we will now proceed, no? So to the next five examples. Okay, so five examples which will be illustrating, no? So the concept of the simple stresses as presented. So the normal stress, the shearing stress, and lastly, the bearing stresses. Okay, so now again, can we take note of the given, no? In each item. Okay, so since we will be shifting from whiteboard screen to the screen wherein you can see the uh, sample problems. Okay, so we have here in example number one. Okay, so in example number one, so you have there what is the required diameter of a steel member. Okay, so if the tensile design load is 7,000 pounds, so assume a safety of 5 based on an ultimate strength of 60 psi. Okay, so this is a very common worded problem, no, involving normal stresses. Okay, okay. So in item number one, okay, so you have the okay as presented. So it's what is the required diameter of a steel member? Okay, so that means the cross-sectional area, of course, that's uh, okay, the circular cross-sectional area because we're being asked with the required diameter. Okay, so you have there a steel member, so whose cross-sectional area is circular. So okay, so this is subjected by a tensile force of 7,000 pounds. Okay, as given. So the ultimate shearing stress given is um, okay. So this is the cross-sectional area. So the ultimate stress, no? So given. So we refer this one to the normal stress, no? Because as presented, so it's very apparent that the area being considered is the perpendicular area. Okay, so the given stress is 60,000 psi. So that's 60,000 psi. Okay, so by formula, we then say that the normal stress, so that's 60,000 psi. So that's pound per. So that is equivalent to force over area. No? So that's 7,000 pounds per area. So for area of a circle, as we all know, so with a given diameter d, so that's equivalent to pi r square, or in terms of diameter, that's pi d square over 4. Okay, so we can have pi over 4 and then multiplied with d square. Okay, so of course this will have a unit in inch square. Okay, so such that if we try to solve for d, so the diameter required, by the way, there is a factor of safety, no? So which is 5. So we just have to multiply it with 5 here. Okay, so 5 here is given as safety factor. No? Okay, so of course, if not given, then you do not have to include, no? So the safety factor. So calculating for D. Okay, so that's uh, so you will have here 0.385. Of course, the unit is in inch. Okay, so we will check now. So if we have the okay, so 0.385 for item number 1. Okay, so okay, so we do not have the 0.6385. Let me check again. Let's go back to the okay. So recalculating again, no? So that's 7,000. Okay, times 5 divided by 60,000 times 4. Okay. Okay, so I think we I think we forgot to oops. Okay. So I think we forgot to include the factor of safety, no, which is 5. So um, okay. So if we include 5, no, so in the solution, so we'll have letter A, no, so that's okay. So that's 0.862 inches inch. So if we include not so the factor of safety, so there is an error, no, upon entering the data in the calculator. So we forgot to include the factor of safety, which is 5. Okay, so you include that one, and then upon calculating for D, you will have 0.862. Okay, so as the answer. Okay, and okay, the next example, so we have number 2. Okay, so number 2, so you have to determine the outside diameter of a hollow steel tube. So again, no, so outside diameter, so that means this is circular, no, in cross-sectional area. Okay, so that's a hollow steel tube, so that will carry a tensile load of 500 kilonewton. So at a stress of 140 megapascal. No? So assuming that the wall thickness to be 1/10 of the outside diameter. Okay, so uh, we will now, okay, so again, can you take note now of the given? So, okay, so for item number 2, so as mentioned, so that's, you have the a hollow steel tube. So this would be the outside diameter. Okay, so this would be the force, no? So the inside diameter. Okay, so the tube, no, is subjected to a force of um, 500 kilonewton. So the force given is 500. So that's tensile. That means its effect is to elongate, no, the given tube. So the stress, normal stress, no, that's 140 times 10 to the power of 6 Pascal, no, or megapascal. Okay. Now, if we try to look at uh, the outside diameter is given to be variable d. Okay. And then the thickness, no, so the thickness, okay, so that's the thickness of the object, no, so that's, or the hollow steel tube, no, so that's 1/10 of the outside diameter. So this would be uh, thickness, and this also be the thickness. Okay, so uh, therefore we may say, no, so we may say that the inner diameter, so we call this one d. So we then say that d, the inner diameter, is equal to outside minus 2 times the thickness. So basically that's d minus 2 times 1/10 of d. Okay, so that's d minus d over 5. Okay, so that's the inside diameter. No? So basically, we then say that the stress, normal stress, that's force, 500 times 10 to the power of 3 Newton, so divided by the area. No? So now, since this is hollow, okay, so take note, this is hollow. So we only consider the area. No? So the area shaded or given with the red color shade. No? So that's the only area that we are going to consider. So, so basically, we can have area. No? So area can be presented by uh, the area, no, of the bigger. Okay, so that's the bigger circle. So with the outside diameter, so that's pi over 4 d squared. So minus the area of this hollow portion. No? So that's pi over 4, and then that's d squared. Okay, so we can have area that's pi over 4, and then d squared minus this one. Okay, d is equivalent to d minus d over 5. Okay, so square. So if we substitute it here, so we can have, so 140 times 10 to the power of 6 Pascal, that's 500 times 10 to the power of 3 Newton divided by, of course, the area. That's pi over 4 multiplied by d squared minus d over 5. So anyway, you can use your calculators directly to calculate for d. Okay. So upon calculating, d would be, so that's, you can use the shift solve function in your calculator, or basically you can solve them manually. Okay, so you can solve, no? So the problem manually. So, okay, so that's, okay, so that's, okay, sorry for that. So basically, I'm using the shift solve function, no, in my calculator right now. So D would be that's 0.112. Okay, so the unit, of course, would be in uh, Okay, so this would be, since we have Newton and then Pascal, so this would be 0.112 meters, no? Or meter. So, or this would be equivalent to 112 mm. Okay, so we'll try to take a look if we have 0.112, no? So from the traces, so okay, so you have there 112 mm, no? So or 0.112 meters, meter. Okay, so that's it, no? For examples one and number two. Okay, so now we go to example number three. Okay, so in example number three, so we are given with, no, so examples number three and number four as samples, no, for sample problem for shearing stress. Okay, so but anyway, let us assume, no, that we do not know, no, that the given problem is for shearing stress. Okay, so because that's the actually that's the actual scenario, no, in the example examinations, or perhaps in your board examination. So wherein you will not be asked, no, whether it is normal stress or shearing stress. All you need to do is to, of course, understand what is presented in the problem. Okay. So in example number three, so you have there three rivets. So are used to lap joint two steel plates together. So the when you say lap joint, so it looks like this one. Okay, so you have the two plates, so being joined together by means of rivet. So in this example, we're given with three. So determine the diameter of each rivet. No, if the maximum allowable shearing strength of each rivet is 53 megapascal. So each of the rivet, no, so will has a shearing strength, no, of 53 megapascal. So assume that okay. So assume the axial load is distributed equally, no, on the rivets. So the load, no, is being distributed, no, in the rivets. So we are asked, no, so determine the diameter, no, so of each rivet. So take note that we are presented with shearing stress, no? So with this, we can already have the idea onto what or which area do we need to focus. Okay, so if we try to look at in example number three, so okay, so again, can you take note of the data? Okay, so we have there in example number three, so you have the two plates. Okay, so this could be the position, no, the two plates. So you have there three rivets, no? So the arrangement, no, is not given, but you can always assume, no, that they are placed, no, in line, no, with each other. So the rivet, no, so will go up to the bottom part. The same thing is true with the other one, also with this one. So if you try to look at the force, no, given is 50 kilonewton. Okay, so that's 50 kilonewton now is the force. So if you try to look at, uh, if we try to separate now the two plates, so you will have this plate, assuming we consider the plate at the bottom. So this would be 50 kilonewton. And then you have there the cross section, no, of the rivets. This one. Okay, so now if you try to look at the scenario, okay, so the area which is being focused is actually the area, okay, of the or the cross-sectional area of the three rivets. This one might as well with this one, no? So these are the area being considered, okay? So according to the problem, the okay, the stress given is 53. No? So we didn't say that the stress, so that is the shearing stress, that's 53 times 10 to the power of 6. No? So unit in Pascal or Newton per meter square. Okay. So we then say that the shearing stress is equal to force. No? That's 50 kilonewton. Okay. So, but we have to divide it with 3. Okay. Because it's mentioned that the force is equally distributed in each of the rivet. Okay. So the area being considered here is okay, so the area that's being considered here is the area per, okay, so that's the area per pivot, which is the circular cross section. No? So that's pi, since this is circular area, so that is pi r square. Okay, so the question is the diameter. No? So perhaps we can have 53. Okay, so that's 50,000 Newton divided by pi over 4 d squared. So wherein d is the diameter of each, no, rivet. So calculating for d, so you will have there, okay, so the answer would be 0.02. Of course, this is meter, no? Or basically, this is equivalent to 20 mm. Okay, if expressed in millimeters. Okay, so let us check now if we have the answer. So that's 20 mm, no, in letter B. Okay, so, and then we go to sample problem number 4. Okay, so uh, sample number 4 is somehow a tricky problem, no, because if you cannot see, okay, so the area that is being considered, then you might get the answer wrong. Okay, so in example number 4, so you have the force of 283 kilonewton is required to punch a hole. Okay, the hole will have a 20 mm diameter. Okay, so through a 10 mm thick plate. Okay, so we are asked to calculate the shearing strength of the plate. Okay, so example number 4. So you have the again, can you take a look at the data, no? Okay, so we can have example number 4. So in example number 4, we're given with plate, no? So whose thickness is given to be. So it is said that a 20 mm hole is to be punched. So meaning to say this part here is to be removed by uh, punching using the force is 283 kilonewton. So by applying a force of 283 kilonewton, so the plate, no, so stiffness is 10 mm. Okay, so and then the diameter, no, so the required diameter is 20 mm. So what will happen here is that after punching, so this part will be removed, no, from the plate. So meaning to say there will now be a hole in this plate. Okay. So the required or the item is asking for the shearing strength. No? So that is force divided by the area. So by looking at the uh, figure presented, so you might be taking a look at this area. No? So the red colored circle, but that is not the case because we are being asked with the shearing strength. But if we are asked with the normal stress, then obviously the area that needs to be considered is the parallel area, which is the area of the circle. No? But since we are asked with the shearing strength, then we have to consider the parallel area. So the parallel area that is being considered is actually the area around this cylindrical part, no? So which has or which is being removed, no, from the plate. So you try to look at, so the height is 10 mm, and then obviously the diameter that is 20 mm. Okay, so if you go back into your geometry, so the area now represented by the uh, cylindrical part, no? So we know that the solid removed from the um, cylinder, no, or the solid removed from the plate is cylindrical form, and then the lateral surface area of a cylinder is given by, so that's 2 pi r, okay, the circumference of the circle multiplied by the height, okay, or basically that's pi diameter and then multiplied by h. No? So we then say that the shearing stress, that's 283,000 Newton divided by the area. Area is, as we all know, so that's pi times the diameter, 20 mm, and of course the height, okay, which is 10 mm. So there is no such thing as wrong if you write the complete given like mm, so millimeter. No? So if you just write it in mm, you might be uh, getting the wrong answer at the end because there is a possibility that you might forget. No? So the suffixes given, no? So like mega, kilo, milli, and so on. No? So it would be better, no, if you just write it like milli 10 to the power of negative 3. So mega times 10 to the power of 6 and so on. Okay. Kilo, that's of course the 1,000, no, or times 10 to the power of 3. So the unit is meter square. Sorry, this is meter. So this is meter and then this is meter. So the unit is in meter square. So the shearing strength would be equal to, okay, so pi times So the answer would be 378.8 times 10 to the power of 6. Okay, so unit in Pascal. Okay, or basically we can rewrite it as 378.8 megapascal. So we know that times 10 to the power of 6 is mega. So that's 378.8. No? So we'll try to see if we have the 378.8 answer from the choices. 378.8. Okay. 283 kilonewton. Okay, so okay, try to um, check now if we have. So that's pi r each. Okay, so I think we got the uh, wrong answer. No, so upon calculation, so we will have actually 450 point 4 times 10 to the power of 6 Pascal. Basically, we can have 450 megapascal, approximately 450 megapascal. So, uh, checking with no, so the choices given to us. So that's 450 megapascal. So that's in letter C. Okay. And here it comes, no? Example number 5. So in example number 5, so this is almost the same as with example number 3. But, okay, so but, okay. So this time we are asked to calculate no, the bearing stress no, in each rivet. Okay. So yeah, there are three 20 mm rivets. No? So the 20 mm rivets refers to, or the 20 mm no, in the statement refers to the diameter no, of the rivets. So, so this is used to lap joint two steel plates together. So each plate is 25 mm thick and 130 mm wide. So the plates carry a tensile load of 50 kilonewtons. So determine the bearing stress in each rivet, assuming that the axial load is distributed equally on the rivets. Okay, so um, okay, we go to the solution no, for item number 5. So the item number 5, so we are given with two steel plates. Okay, and then the other one. So the steel plates, no, so it's being lap joint. So there are three rivets, no, so which is used to lap joint. So it passes through, going to the bottom. Okay, so same way with the other one. Okay, so now if we remove, no, so one of the plate, no, for simpler analysis, let's say we consider the plate, no, at the topmost portion, okay, or the upper plate, no, so we can have this one. So you have there three rivet. So since we are asked not to obtain, no, so by the way, the force is 50 kilonewton. So if we try to ask for the bearing stress, so we need to take a look at the projected area. Okay, so now if we cut this one into, or if we cut now the rivet into half, so you will see that uh, it will be look like uh, this one. Okay, so this would be the case. No? Okay, so this would be somehow the illustration. No? So wherein you might be considering the area shaded, no, or the shaded area. So because we are, or we will be after with the projected area. So this one, so this would be the projected area. So if we project this one, or if we try to look at the front view, so this will be projected like this one. Okay, so this one will also be projected. Same thing as with this one, no? So if we try to look at the, okay. So these are the projected area, no? So of the rivets, so we can have uh, the length here, the dimension. So this would be 20 mm. Okay, so this one 20 mm, and then the height, the thickness, no? So this one. Okay, so this would be equal to um, okay, 25 mm thick. Okay, so now if we try to look at, okay, or if we try to analyze again, now, so the three stresses. Now, if the problem is asking for the normal stress, so the same thing, force over area. But the area that is considered is the perpendicular area. Now, which one is the perpendicular area? So this one. No? So this would be the perpendicular area wherein the force is subjected to the force F. Okay. But if asked for the shearing stress, no, so let's say the shearing stress, the force over area, then the area that needs to be considered is of course the parallel area. So the area that holds the two plates together is actually the cross-sectional area, this one. Okay, so uh, but if the bearing stress is asked, no, so that is the projected area, okay, of the rivets, no, so making it this area. Okay, so this would be three area. So then therefore, if we try to use the formula, okay, so if we try to use the formula, then the bearing stress force, that's 50,000 Newton. So divided by 3 because you have the 3 rivets, no? And then projected area, okay, so that's equivalent to uh, this area here. That's area of a rectangle. Okay, so length times width. So area is 25 mm. So times 10 to the power of negative 3. And you have there 20 times 10 to the power of negative 3. Okay, so the bearing stress would be equal to, so you have there 33.33 times 10 to the power of 6 Pascal, or basically 33.33. This would be mega. Okay, so that's the bearing stress. No? So in example number 5, so you have there 33.33 megapascal. Okay, so after which we move now so to the next topics that we have. Okay, so which is the thin-walled pressurized tanks. Okay, so we'll just read some definition. No? So a tank or pipe carrying fluid or gas under pressure is subjected to tensile forces. No? So which resist bursting, develop across longitudinal and transverse sections. So we will be considering um, two types now of container. So we have the cylindrical tank and the other one, the what we so called spherical tank. Okay, so spherical tanks, this one. Okay, so uh, we denote no so the term thin wall. Okay, so we denote thin wall if as given, no? So that's the thickness is equal to 1%, no? Of the inner radius. So that's 1% or less, no? So to the inner radius. So for cylindrical tank, so we have these two types of stress, no? So that can be developed. So you have there the tangential stress, and we also have the longitudinal stress. Okay, so okay, so for tangential stress, so that is equivalent to the inside pressure multiplied by the diameter over 2 times not the thickness. Okay, for longitudinal stress, so that's the inside pressure. Okay, so uh, multiplied by the diameter no, of the tank divided by 40. So if you try to look at the spherical tanks, no, so it may experience now these two types of stresses. So if you're not given with as to which type is the stress given, then you have to consider the two. So both the tangential and the circumferential and the longitudinal stress. So all you need to do is to memorize this formula, substitute, and that's it. No, you can have the solution no, for the problem. Whereas for spherical tank, Okay, so the stress developed, no? So that's equivalent to the pressure. So we'll have it pressure inside the tank multiplied by the diameter, okay, and divided by 4 times the thickness, no, of the tank. So, okay, so only the cylindrical tank, no, may develop the what is so-called tangential or the longitudinal stress. Okay, so okay, we have in example number 6, no, number 7, so which focuses on the spherical, no, and cylindrical tanks. Okay, so example number 6. Okay, so you have the cylindrical water reservoir. So 12 meters high and 8 meters in diameter. So this is to be completely filled with water. So find the minimum thickness of the reservoir. Now, so plating, if the stress is limited to 40 megapascal. So yeah, no, you have there the cylindrical tank. Okay, so the stress now is limited to 40 megapascal. Okay, so and then the tank now is filled with water 12 meters high. The diameter now is 8 meters now in diameter. So we are asked to calculate the minimum thickness of the tank if the stress is limited to 40 megapascal. Okay, so uh, let's try to look at number 6. Okay, so okay, again, no, can you take note of the data? Okay, so okay, so we have item number 6. Okay, so okay, for item number 6, so we have the cylindrical tank. Okay, so um, we're given with, no? This would be the cylindrical tank. So this is full of uh, the liquid, no? So water is given. Okay, so the height, no? As given that's 12 meters and the diameter, no? The tank is said to be 8 meters. So this is full of water. So we are asked to obtain, no? So the minimum thickness. Okay, so if the stress is limited to 40 megapascal, so the stress is just limited to 40 megapascal. Okay. Now, if we consider the tangential stress, no? So first is we consider tangential stress. Uh, okay, so we have there 40 megapascal that is equivalent to the internal pressure multiplied by the diameter, no? 8, and then um, okay, so that's um, divided by 2t. Okay, so this would be 2P. And then letter B, we consider the longitudinal stress, no? So you have there 40 megapascal, that is the internal pressure multiplied by the diameter divided by 2P. So now how do we calculate for the internal pressure? So pressure due to a column of uh, fluid that's equivalent to specific weight, no, of the fluid multiplied by, of course, the height. So in this case, that's since this is water, so that's 9810 Newton per cubic meter. Okay, so multiplied by the height, which is 12 meters. So this would give us the internal pressure as okay, 1,117,720 Newton per meter square. Okay, so we can then say, no, so that this is equal to okay. So calculating for t, so substituting this value here, so we can calculate for t, no? So that's times 8, okay, divided by okay, so the okay, so by the way, this is 40. Okay, so that is um so t here would be around 0.0118, or basically t is equal to 0.012 meters. That is equal to 12 mm. Okay, so considering the longitudinal stress, so the same pressure, no, same internal pressure, but we consider the longitudinal stress. So we can calculate for T. That's okay. So that's 5.9 times 10 to the power of negative 3, or basically P is equal to 6 mm. Okay. So if we try to look at which of the thickness is the minimum required thickness, no, for the given tank. Okay. Now, let us say we consider 12 mm. Okay. So let us say we consider 12 mm. So for tangential stress, the stress developed is 40 megapascal. Now, we try to substitute T here. But if we try to substitute T, no, so in this formula, so the longitudinal stress is equal to P times 8 divided by 4 times 4, that's 0.012. Okay. So this would be equal to uh, okay, so that's 117,720 times 8 divided by 4 times 0.012. So this will result to answer of 19.62 megapascal. So which is okay since uh, the maximum stress is 40. But if we let's say, thickness to be 6 mm, okay? So 6. thickness. So if we substitute it here, so you will have internal pressure 117,720 times 8 divided by 2 times. 2 times 6 mm is 6 times 10 to the power of negative 3. So that will give us 117,720 times 8 divided by 2 times 6 exponential negative 3. So you will end up with around 78.5 megapascal. So which is way bigger as compared to the limit, which is 40 megapascal. This one. So therefore, the minimum diameter, okay, so the minimum diameter for this tank is equal to 12 mm. Okay, so we do not decide based on the number, no, by saying 6 mm is smaller than 12 mm. Okay, so we have to consider the scenario as presented, no, longitudinal stress and the tangential stress. Okay, so which one can pass, no, or uh, can pass, no? So the maximum stress, then that would be the final answer. Okay, so that's for item number 6. Okay, then we go to, let's try to take a look at the answer, 12 mm. So we have to, or we'll try to look at, no? So if we have there 12 mm, no, in our, okay, so you have there 11.77 mm or around 12 mm. Okay, so number 7, so you have there the spherical tank, no? So this is used for storing gas under pressure. Uh, okay, so that is 25 meters in diameter and it's made of 15 mm thick. No? So the yield point of the material is 240 megapascal. So a factor of safety of 2.5, no, or a factor of safety of 2.5 is desired. So what is the permissible internal pressures? This time that's spherical tank. Okay. So for spherical tank, so this is a very straightforward example. Okay. So you have the spherical tank. Okay. So the pressure, the internal pressure inside, no, so will cause uh, a stress of 240 megapascal. So this is the internal pressure inside, no? So denoted by variable P. Okay, so that's the stress is equal to, so the internal pressure multiplied by diameter D. Okay, that's 25 meters. Okay, over 4 times the thickness uh, given is 15 mm. So this is 15 mm. Okay, so such that P, by the way, factor safety of 2.5 is included. So you have to include, no? So the 2.5 P then that's equivalent to, okay, so divided by 25 times 2.5. So P then, internal pressure must be 230.4 unit in kilo Pascal. Okay, so it's 230.4, no? So we'll try to take a look at if we have the answer. Okay, so you have there 230 kilopascal. Okay, so that is the internal pressure. Okay, so and then we go to the next topic. Okay, so next topic is elastic deformation. No? So we define the following items or terms. So first is the strain. Okay, so strain is the ratio of elongation to original length. Okay, so we have this formula. Okay, so the strain is the ratio, no, of the elongation to the original strength. I mean original length. Okay, so we have the following, no. So uh, an object, no, so may tend to stretch, may tend to elongate, or it may tend to constrict. So either, so the first scenario is an object may tend to constrict or may tend to elongate if an extra load is applied. Okay, so may it be that the object's being applied with external load, so it may tend to stretch or it may tend to constrict, no, if that is given, no, with compressive load. Okay, so the elongation, no, so the elongation denoted by the variable, so that's PL over AE, no, so wherein P is the applied force, L is the original length, A is the area, E is of course the proportionality constant or the modulus of elasticity. So we will be using these values, no? So 30 times 10 to the power of 6 psi or 210 gigapascal. That is for steel. Otherwise, if it is made of other materials, then E must of course be given. Okay. So whatever the value of E presented in the problem, so you'll be using that. No? So unless otherwise, if it is mentioned steel, which is the most commonly used metal, no, for some or for problems like this one, then you have to use 30 times 10 to the power of 6 or 200 gigapascal. Okay, so in example number 9, okay, so you have the a load, no, of 20 kilonewtons. So it's suspended vertically, no, from a steel rod. So you have the steel rod, so with the load in it, also attached. So the load is 20 kilonewtons. So the cross-sectional area is 300 mm square. No? So the total length, no, of the steel rod is 180 meters. So apart from the external load, so the rod weighs also, no, it weighs 77 kilonewton per cubic meter. So the modulus of elasticity is provided, no, that's 200 gigapascal. So determine the total elongation of the rod. Okay, so so the rod, no, so in problem number 9, okay, so you have their a rod. So it's not mentioned, no, if it is circular or it is rectangular or square. So the rod is 180 meters. Okay, so although 180 meters is too long, but then since that is the given in the problem, then we have to use it meters. So in the rod, so there is an attached load of uh, okay, so 20 kilonewtons. And then also another load indirectly, no, another load because this may act also as a load. So that is the weight of the rod. So that means the total load of the rod, P total. No? So this is total force experienced by the rod. That's 20 kilonewton plus the weight. Okay. So we then say no, so that the weight of the rod that is equivalent to, okay, so that's 77 kilonewton per cubic meter, kilonewton per cubic meter, so times the volume, okay? So wherein the volume, so the volume is, so if this is the cross-sectional area, so the volume can be calculated as the area times the length. Okay, so that is 77 times kilonewton, no, per cubic meter. So that's the volume that is uh, area, no. So what is the area given? That's 300 mm square. Okay, so the area is 300 mm square. So you must convert this one into meter. So you will have 1 meter, so 1000 mm square. Okay, so this is the area multiplied by the length. So length is equal to 180 meters. So of course you can cancel out the mm square, mm together with this one, no? So you will have then an answer of 77 times 300 divided by 1000 square, okay, times 180. So the weight is 4.158 kilo Newton. Okay, so therefore the total load attached is 24.158 kilonewton, or basically that's 158 Newton. So to calculate for the elongation, that's PL over AE. So that's P, so 24,158 Newton. Length is 180 meters. A, okay, the area is given to be 300 divided by 1000 square. So this is the area. E is uh, 200 gigapascal. 200 times 10 to the power of 9. So you have there, so the total elongation is 0.0725 unit in meters. That's 0.0725. Okay. Okay, so the elongation now is 0.0725 meters, or that's 72.5 mm. Okay, so okay. Okay, so as you can see now, so we do not have 72.5 mm. Uh, I'll just give it to you, no, to uh, recalculate again the process. Okay, so and then perhaps we have encountered, no, some typographical error, no, upon inputting the data, no, in the calculator, but the process now would be the same. So all you need to do is to recalculate it, and if the answer is 72.5 mm, then that is the final answer, of course. So there may be some typographical error in the choices provided. Okay, so okay, so the next item, so in relation to Hooke's law, so we have the elongation, no? So the axial elongation, okay, or deformation due to the change in temperature. Okay, so using the formula, no, so the elongation, so that's equivalent to the coefficient of linear expansion of the body. So we're given with the variable, no, for steel, that's per degree Fahrenheit or per degree Celsius. Okay, so multiplied by length, so that is the original, of course, not the original length, and then we have the delta T, no? So the change in temperature. Okay, so okay, so that's for elongation due to the changes in temperature. Okay, so we now go on to example number 10. Okay, so in example number 10, so we are given with, no? So let's see. Okay, so in example number 10, so you have there a bar of length 120 inches, now is prevented from expansion or contraction. So by rigid end restraints. So find the stress induced. Okay, so by a temperature rise of 60 degrees Fahrenheit, use alpha equals to 8 times 10 to the power of negative 6 per degree Fahrenheit, and E, okay, so that's 20 times 10 to the power of 6 psi for steel. Okay, so okay, we can illustrate, no, item number 10 using, okay, so for item number 10, so we are actually given with um, a bar. So this is the metal bar. So the metal bar is uh, okay. The metal bar is subjected to, okay, so a temperature rise of 60. So this is subjected to delta T, which is equal to 60 degrees Fahrenheit. Okay, that's T2 minus T1. So now, since the temperature increases, so supposedly the bar will tend to elongate. Okay, okay, so this is supposed to elongate. However, so the bar cannot do that because, as mentioned, it is placed with n. Uh, okay, that's end restraints. No? So preventing the bar to elongate or to constrict. Okay. Okay, so this is the end restraint. So it actually holds the bar. No, it prevents from elongation. At the same time, it prevents the bar from constricting. Okay, so the bar cannot um, elongate. No, so we are asked to obtain the stress. Okay, so the bar supposedly will elongate now because of the change in temperature. So you have the elongation, that's alpha um, L delta T. Okay, and then delta T. Okay, so this is supposed to be the elongation, no? So due to the change in temperature. However, because of this end restraints, so this somehow push, no, the bar with a force P. Somehow the end restriction poses the bar, okay, or poses actually a force P that counteract with the supposed to be elongation due to the change in temperature. So the elongation is also equivalent to the constriction. So the force P somehow constrict the bar from elongation. So as we all know, so if you have there an applied force, the elongation is equivalent to PL over AE. Okay, so uh, we can equate, no? So we can cancel out L such that we have, okay, the resulting expression. So alpha delta T, so that is equivalent to P over AE. And we know force per unit area is stress. Okay, such that we can have the alpha delta T times E, that's equivalent to stress. Okay, so if we try to multiply, no, all the remaining data, so we have the alpha 8 times 10 to the power of negative 6. Okay, so that's 8 times 10 to the power of negative 6 per degree Fahrenheit. Delta T is 60 degree Fahrenheit. And E, of course, now E is 20 times 10 to the power of 6 psi. So 20 times 10 to the power of 6 psi. Okay, so that's equivalent to stress. So calculating then, so will give us an answer of, so this would be 9,600 psi. Okay, now so that's 9,600 psi for item number 10. Okay, so let's try to take a look at the choices. Okay, so here you are now. So 9,600 psi. Okay. And then we go to, no, so we go to the next topic. Okay, so that is the okay. So we have the torsional stress. No? So this time, this is the stress developed when a body is being twisted. No? So just a while ago, we introduced, no, the stress uh, develop, no? So possible there is a stress develop, no? So when it is being, or when a body, no, is subjected to load, okay, so there is a stress develop when the body is subjected to uh, change in temperature. Okay, so this time, so we will be examining the stress developed also by a body when it is subjected to uh, torsion. No? So meaning to say it's subjected to twisting. Okay, so we'll just run through the formulas. Know that these formulas has to be memorized. Okay, and one way to memorize or familiarize, no, with the formula is of course to keep using, no, so the said formula. So by applying it to some sample problems. Okay, so we try to look at, we have here the torsion stress for solid shaft. So that's kindly take a look at the formula. 16 times the applied torque divided by pi d cube. For hollow, so you have there 16. No? So times td is divided pi d to the power of 4 minus the smaller, or the inner radius, I mean inner diameter, not to the power of 4. So, and then the power, no? So power delivered by a rotating shaft. Okay. So you have the 2 pi nt, no? So that's n is the speed. Usually, if given in terms of RPM, okay, so okay, usually if n is in terms of RPM, which is most likely the case, then this will be over 60. So power then is 2 pi nt over 60, unit in watts. So without the 60, no? So uh, okay, this would be okay. So we'll just have to correct this one. Okay. Um, so power then would be equal to, okay, so this would be over 60. So this would be in RPM, and torque, of course, in Newton meter. Now, so 2 pi nt over 60. That's the power developed, no, by a rotating shaft. So whether it is solid or um, hollow. So next is the twisting angle, no, of the shaft fiber. So this is the how do we call this one? The if a body is being twisted, so there is a possibility that the body, no, so will be deformed. So it will be twisted by a particular angle. Well, we call this one angle theta. Okay, just like uh, the figure represented. So we can calculate for theta. So that's the applied torque multiplied by the length divided by uh, J, and multiplied by the denominator multiplied by the modulus of rigidity. No? So J, by the way, is the polar moment of inertia. Okay, so for solid shaft, that's pi d4 over 32. For hollow shaft, so you have also this formula. Okay, so uh, the modulus of rigidity, no? So can be calculated. No? So that's E over 2 times 1 plus mu. So wherein mu is said to be the Poisson's ratio. Okay. So, but if it is given, then no need to calculate for the modulus of rigidity. So we are given here with modulus of rigidity for steel, that's 11.5 times 10 to the power of 6 psi or 80 gigapascal. No? So unless otherwise given. So we now use the formulas presented, okay, to calculate for the items being asked in the next two examples. Okay. So again, all you need to do is memorize the formulas, familiarize them, okay, and then you will be ready, for mechanics of the deformable bodies. Okay, so let's go on to item number 11. Okay, item number 11 states that, okay, so you have there a solid shaft, so having a diameter of 1.5 cm. Okay, so it rotates at 1,800 RPM. So the allowable torsional shearing stress is 50 megapascal. So what power in kilowatts? So the said shaft can transmit. So it's actually a combination of formulas, no? So we'll try to, okay. So that's item number 11. Okay, so that's solid shaft. So the diameter of the solid shaft is 1.5 cm. So this is equivalent to point, okay, uh, so this is 0.015 meter. Another given from the problem is that the speed is 1,800 RPM. Okay, and then the allowable stress, no? So that's 50. So we are asked for the power, no? So power developed, no? So power that can be transmitted. Okay. So we know that power is equal to 2 pi nt divided by 60. So only if we are provided with the torque, no? So then we can calculate. Okay. So however, we're not given with the torque, so perhaps we can use the stress formula, no? So this one. So S is equal to, okay, so that's 16T over pi d cube. Okay, so 16T divided by pi d cube. No? So we can have 50 times 10 to the power of 6. That's equivalent to 16T pi and then 0.015 cube. So T then can be given as 33.13 Newton meter. So substituting directly, so that's 2 pi n is 1,800, 33.13 over 60 power then is 6,244.9 watts. Okay, so or 6.24 kilowatts. No? So that would be for item number 11. 6.24 kilowatts. Okay. So, okay. And then we have item number 12. Okay, so item number 12. So you have there a hollow shaft, hollow steel shaft. So hollow. So designed, okay, so to transmit 500 HP at 18,000 RPM, 1,800 RPM. Okay, so if the outside diameter of the shaft is 3 inches, so how large may the inside diameter be so that it will not exceed to a shearing stress of 10,000 psi. So we are asked not to obtain the internal diameter, no, so that it will not exceed to 10,000 psi. Okay, so again can be have the data. Okay, so you have their okay. So this is the hollow shaft to the given R. No? So power, that's 500 HP. Um, Speed, that's 1,800 RPM. Um, Outside diameter, no? That's 3 inches. Okay, so the inside diameter is unknown. The maximum stress is 10,000 psi. Okay, okay, so that's so we all know, no? So we know that power is equal to 2 pi NP divided by 60. So for it to be in watts, so torque must be in Newton meter. Okay, so and since we are using English unit, so we may use, no, so additional formula instead of power, so that's HP, so that's 2 pi NT divided by 44760. So torque in Newton meter, or HP equals to 2 pi NT divided by 33,000. Torque is in foot pound. Okay, so we're using foot, no? Okay, so therefore we can calculate the torque. Okay, so that's 500 HP. That's 2 pi n is given directly divided by 33,000. Torque then is equivalent to, so the answer is 1,458.92 foot-pound. Okay, and the stress, no? So stress, uh, okay, so the stress is given by that 16 dB. Okay, so we can just substitute directly now. So you have there 10,000. So since we are using inches, no? So we need to convert this torque in terms of inches. No? So therefore, so perhaps you can multiply with 12 inches per 1 foot. So Torque would be, okay, torque would be 17,507 point. Okay, that's 17,507. Unit is of course in inch pound. Okay, so stress, no? So that's 16 TD divided by pi. Okay, so this would be 10,000 PSI. So that's uh, pound per inch square. Okay, so that's 16 times 17,507 point. Okay, that's inch pound. Okay, so pi. So D is 3 inches to the power of 4 minus D to the power of 4. Okay, so uh, we can cancel pound and then perhaps, no, so we can uh, okay, so we can um, okay, there's still lacking 16 TD. So that's 3 inches here. So, okay, so inches times inches multiplied by inch square. So that would be inch to the power of 4, right? So, upon calculating D to the power of 4, so that would be, okay, so the 16 times 17,507 times 3 divided by 10,000 times pi. Okay, okay, so do not be mistaken with 3. So that's 3 to the power of 4. No? So, okay, so 3 to the power of 4. So D here can be calculated as 2.713 inches. Okay, so and you have there, okay, that's 2.714 inches. Okay, so that would be for item number 12. Okay, so